Uh,
Is it better there?
Mhm.
Yeah, no, that's clear. Great.
all right, good.
Awesome.
Okay, well, it's great to get us all together. Very nice. See you all around the table. So this is to supplement what goes on every week when I come down to the lab and talk to everybody individually. But it's kind of nice. The group has gotten big enough and diverse enough that I think everybody would benefit from a forum where you kind of learn in a capsule bit what everyone's up to. And also, I'd like to use this forum as a place for people to kind of give us slightly more formal presentation on their work. You can all need practice doing that. And it would be also a very good way as we rotate through everybody in the group, for everyone to get some experience presenting a bit of new observations that they've made. So I think we'll start out these group meetings, but with just some informal discussion about maybe something to reflect what's on everybody's mind, scientifically mostly, but also would be a place to ventilate other issues like, missing optics or missing extension cords or burned coffee or something like that. Anything is fair game. So, and I kind of have a pretty good idea of what everybody's doing, but I'd like to know what you think you're doing in a sense. I mean, what your priorities are and what you see your big picture interests are as that's useful for me to know, and certainly it helps everybody else know what's going on. So I can start us off by talking just a little bit about what I've been up to the last over the weekend and a few days before that. So I've got the Air Force proposal out of hibernation, and I've gone back to it to polish it up. And the section that needed to be finished related to the theoretical work that Rushi has been doing in collaboration with John Sues and Abhinav Prem, a postdoc at Princeton. And so we work experimentally, on the dark side of the lab, the plasma experiment. We end up with a system of about several million random dipoles that are probably ultra cold in this little assembly. And it has some interesting quantum mechanical properties. And Rushi has tackled the task of representing that theoretically, but he's had to work with a little bit smaller size system than spins. He's worked with 11 spins and looked at what happens when you put those 11 spins in a disordered environment and cause one of them to dissociate. And it's a complex system, and it communicates in this complex system and it decays. And his work represents the theory of that, and it relates to what we see in the experiment. And so I've been honing our perception of this and getting it written down in the proposal. And so that's occupied a lot of my attention for the last little while. I haven't had a lot of time to think about other things that are going on. But in terms of unique perspectives, Eric, I think you're the one that's been outside the lab working with Sabrina Leslie. What sorts of things are you doing? What's your big vision of that?
Well, right now I'm trying to understand their system. So they have a click scope, which is generally very new to me. So try to understand how the system works, how I can take data.
Mm-hmm. So what kinds of have you started to make measurements?
Yeah, already just like a week into it.
And it's DNA is what you've got in there. So you're looking.
So basically, we try to measure binding rates between oligos and plasmids.
Hey, Sarah.
So we have prepared oligos, and then what we are doing is that we want to put them together and see they find.
And so the click, what click stands for is
Convex lens
convex lens induced localization or something like
confinement.
confinement. Oh, complex lens induced confinement, yeah. So they take a slide that's etched on the bottom, and then when they bend the system, it smooshes it down in such a way that it makes a bunch of little compartments.
Yes.
You can isolate reactants in those compartments.
So actually, we have they've etched arrays, micro arrays on normal cover slip, and then they create pit holes. So that is where the binding samples go to. So you add a convex lens, and what it does is that it creates this confinement. You release it, and then the oil sample flow off, just like flow cytometry.
Do you know what kind of size range do they use for?
5 nanometers deep for the wells, and I think it's 3 microns.
But what about the molecules or
Oh, those are very small.
are they? I guess I'm wondering, are they much smaller than what we look at? Like
Very
less than single digit
Yeah,
nanometers?
they're fragments of DNA right now. Yeah, so it's short DNA oligomers. And they're super coiled, so there's some kind of
Yeah.
And the trick is that you could put a dye in one place and a dye in another place. And if they coil in a certain way, that the two dyes interfere with each other, interact, and that produces a color change. So that's interesting. You said they're 5 nanometers deep.
The wells, yes.
5 nanometers deep.
It's very, very small.
So that says something about what interference effect that might have. I mean, that's too short a distance to matter as far as the interference of light. It's going to look like basically one surface.
I think that.
Yes.
And that's tunable too, right? They could probably make it.
Yeah.
Okay.
They have several.
Yeah, we'll have to look at that and talk more about that when we get closer. But the idea is eventually to try and make a combination of iSCAD and click. That is to use this interferometric detection with confinement. And it's really how you handle the reflection that comes from the upper surface that's going to make it.
Yeah. That's a long.
All right, interesting. So Rushi, what are you up to?
Okay, so think about it to explain. So that you can all understand. So if you as you know, we're working on the plasma system. But currently, we're trying to use a theoretical approach to study the quantum mechanical feature. So maybe you guys have learned the quantum chemistry or quantum mechanics in your classes. So even though Schrödinger's equation, that's basically governs the equation of motion in the quantum system. But that works for a closed system, which means the energy of contract. But here we want to study the open system property. So that's kind of match what we observed in the experiment. So we use the millimeter wave to drive a dissipation, so that some revert molecule just decay to neutral atoms very fast. So that's kind of an open system. So for the open system, you can have the similar rule. It's called a Lindblad equation or Lindblad dynamics instead of the Schrödinger dynamics. So that's basically I'm just looking at the equations for
What was the name of that again?
the Lindblad.
Can you spell that? I'm not.
So LIN B
That's LIND.
So LIND BLAD.
Oh, okay.
Yeah, so basically a Schrodinger equation is kind of equivalent to the Heisenberg equation, just solving the, but in a different expression. So, but the Limblad is just adding another term for the dissipation to the keyboard. That's for an open quantum system. So, but the difficult for solving that is for the many body problems. For example, if we have many spins, we just the Hilbert space. You heard about this Hilbert space in your quantum mechanical class. So the Hilbert space has a very huge dimension. So for each spin, you have the dimension of 2, right? But you have 2 spins, you have 2 to the 2 is 1. But you have n spins, you have 2 to the n. So basically the matrix size will scale by the power up. Yeah. So that's the difficult for solving a large system. So far the maximum we can go is for the classical computer is 2 to the 11. Yeah. And for larger system, we have to use some other numerical approximation or use the quantum. That's kind of quantum simulation where we like using a classical computer to solve the quantum.
I think there's also a problem where, like, even if you had a quantum computer, you don't have enough bits to represent everything as well, right?
But yet, when you look at it, I mean, it's just like vision. You know, we all are looking around the room and we're processing millions of pieces of information, and perhaps some of it even coherently is going through our brains. And we've got all of these, all of these chances. So it's not impossible to imagine something like that. We have the bandwidth in certain respects to deal with massive problems, but it's just that we're limited in the formal way we represent. So the sociological story, I think, with what Rishi is up to is an interesting one, in the sense that when John and I were working together to make those models that we published in Neutron Law Physics and TRL, they were entirely conceptual models. There was very little that you would point to and say, this is a numerical solution of something. And we mostly just said, here's some equations, and here's some ways that we expect these equations to behave. And we had a few little calculations that we did for sort of normal kinds of atoms and molecules you might encounter, just to give a rough idea of how large certain dimensions of the space were. But by and large, it was all just hand waving and a kind of physical argument. And what Rishi is up to now is that he can actually say something concrete and have a simulation that's real, using a kind of an approximation of the dynamics. And it really does, it is, this Lindblad business is really neat, because you take this, if you take a closed system, and no matter how complicated the Hamiltonian is, you can imagine what the closed system is going to do. It's just going to sit there and reside in a state. There'll be some state of the closed system, as long as there's no information flowing in or out, or energy flowing in or out, that's a stationary state. And so it just oscillates at whatever its frequency is. But with respect to any reference that you might want to measure it against. What the Lindblad equation does is it says, all right, let's consider that as a kind of a place to start. And then we'll introduce these jump operators, which are the perturbation that would occur from connecting to the outside world. And the Lindbladian includes this Hamiltonian part and this jump operator. And it works for 11 spins. And actually what you see is not far different from what we see in the experiment. If you convert everything into real-time units, that the system kind of behaves like the experimentals. Yeah. So anyway, I mean, this is a big step forward, and now Suze and Prem and Sebastian and Pekka in Munich, they're all theoreticians who are excited about doing real big scale calculations on this. So that's really going to be a big boost to the program. So these are complex systems that are like what everybody else's complex systems, but they just happen to be in the gas phase in the other lab.
Yeah, I thought I was understanding it before, but it confused me a lot. So maybe I'm sure I'm not going to understand it today, but is it that the Hamiltonian solution was not able to give a proper demonstration of a
No, you only know that there does exist a solution. You can't actually figure it out for the real system. It's way too big.
Okay.
Yeah.
So what does the Lindbergh equation add?
It's a way of working on smaller systems, but getting numerical results out. So you don't have to have a supercomputer to do it. You can run and make predictions about, you know, if I cause this site to, if I've got a system that's frozen in place because of disorder, and I cause one state to dissociate, how does that translate across the system? And the answer is not obvious how that should happen. But we see in the experiment that it does dissociate, it does spread. We see evidence that it's localized, and then when we turn on dissociation, we see evidence that it just decays. And so we think we see it with nature's own analog computer. And what Rushi's been able to show is that it works with a little toy model of the same thing. So we move from models of plasmids, beating plasmids, to models of beating hearts, right?
I guess so. So yeah, the last little bit I've been working primarily on our electrophysiology project, and it's something I don't think I've ever really formally given a presentation about with anybody. So if that's something that's interesting, maybe even for the next one that we do, I can
Okay,
go
good.
through and just talk about that. We've got tons of slides and information that we can do on it, but just a quick talk about what I did. Our algorithm takes raw ECG scans that are over the course of anywhere from 5 seconds to about a minute long, and reduces the dimensionality down into what's called a representative heartbeat. And we use that to as a basis for predicting a diagnosis of Brugada syndrome, and that takes time. Using wavelet transform is really effective, and you get a really high accuracy, but it takes a very, very long time to actually do a full frequency and time analysis on it. So the last little bit I've been working on an autoencoder that is able to perform this operation significantly faster. And we've had a lot of success with it. So instead of taking 40 seconds to do it on an ECG scan of around 8 to 10 seconds in length, it now does it in about 60 milliseconds. So it's 600 times improvement, but the important number is that it can perform this operation faster than it can stream the data in. So the idea here is that we can move this algorithm into the domain of wearable devices and stuff for online streaming. So been dealing with primarily a decision threshold. So the output of this autoencoder is basically a bunch of sticks that indicate where an R peak might be, but sometimes you get false positives as well. So found out a way using the gradient of the ECG to discriminate against some of the peaks that we're actually not interested in without really adding any time for the actual calculation. So I can talk about that next time.
Yeah, that would be really
Everybody's
good. I think
interested.
this is a really nice illustration of how thinking about spectroscopy and thinking about molecular systems maps onto a different part of the real world, and you can extend this thinking, and it's not really a big reach to go to solving different kinds of problems.
That's basically me for the last little bit though. I'll pass it off to Sarah here. Yeah, I can get it up on this little headstock.
Sarah, we've got a meeting on Friday. You remember with Paul Bishop.
I have 3 ongoing projects. One of them is for Terra company. It's basically the instrument that we designed, Ginger, Luke, Ed, and Massa. It's a group project that they're working on, and it was for taking out the spectra from the materials that they have, the big fluorescent that suppressing all of the peaks inside the raw one. So for a year, we've been working on this. Ginger was designing the instrument itself. I was programming the lab V1 interface, and I'm working on the data collection part of it, and NASA is working on the simulation part, and Luke was supervising everything. So we're in that step that we're collecting the data from the instrument, and then we're working on the data extraction and feature selection part of it. And Masa will explain about it later. So this was with Terra company. They have 2 other projects with Canfor. One of them is about data fusion. So basically what we're doing right now is extracting the information that we have from Raman spectroscopy, and then combine this information with another technique, which is called extract eye or pulp eye. And basically that method is just extracting the information about the morphology of the cellular samples and pulp itself. So we're just combining these 2 information from these 2 separate platforms and making some models to predict the target or the properties of the paper that they're doing mechanically, and it takes a long time to count for. And for the last project, or my thesis project, we've been working on the image analysis of all band papers. So there are some impurities called shies, and this is cellulose glued together, and it just decreases the quality of the papers in the industry. So we designed a light box that takes picture of the pulse and also handshakes that they're making in Canfor to find these shies by just looking at them by eye and circle around them manually. So we're just trying to make everything automatically for them, not go through the very long experiment to just make these handshakes. It takes like 10 days to report the number of shies, while the stack of the papers are being sent to the other companies and industries, and they're using that. So we're just trying to automate this.
Yeah, it's again, it has a sociological dimension too, in a way. I mean, when I say sociology, I mean the human interface, and part of the human interface here is that we want to prepare cultivate our relationship with Canfor in such a way that they're wholeheartedly supportive of an alliance grant that will bring lots of money into the group. And so the proposal for that is written. I'm just waiting for the tender moment to get Paul Bischoff to sign the forms authorizing the contribution from Canfor, and then that goes in and it'll surely be funded. So this will bring a good amount of money into the group for us to do creative things, having to do precisely with this problem, which I think is an important problem, but also other dimensions as well, to do other things that are more curiosity driven and represent instrumental advances that may be somewhat distant from the actual problem. It's a good formula. I mean, this kind of mixture of purposeful research and sort of frontier stuff. I just go to the next one.
Yeah, so I'm currently working on investigating gas nucleation activity of different microplastic samples, and I'm especially interested now in the nanofraction. So we bought from a supplier from Canada different plastic material, like microplastic material, and I've developed like a filtration system where I go down to nanometer size particles and test it for ice nucleation activity. And with ice gas, I aim to get a distribution of those particles, and Simultaneously, I'm running some aging experiments, so I want to know when these nanoparticles would be in the atmosphere and they were aged under oxidative environment and in light, whether they change their ice nucleation activity. So far, I have just started with polypropylene and ozone, and it seems that it's quite stable, so the nucleation didn't shift. But what I observed, I was like, so I actually applied for a conference in Denver, and I got a talk, by the way. So I will give a talk about this nucleation behavior of microplastics. And so last week I started to take some Raman of the raw material, like to collect the purity data, and I found that the polypropylene, the peaks look rather bizarre. So currently I'm kind of like trying to figure out whether the company has have some additives in there. I don't get hold of them. I shared this sample also with my colleagues in Vienna. They do a fluorescence study on them. So they are also measuring Raman this week, and then we will compare whether I got contamination into the sample or whether it's it could be that it's additives or something, so that it's not pure polypropylene, but I need to figure out soon because I need to know whether it's polypropylene, which nucleotides, or rather some other
Surfactant or
organic.
something.
Yeah, exactly. So yeah.
You know, we have somewhere in the lab, we have a vast store of standard materials, and I'm sure we have some polypropylene from various different sources, and some of it's aged,
Yeah,
and other polypropylene is probably pretty close to what it would be like new.
I mean, I can look at the aged one, and it looks very, yeah, it looks very different from like how polypropylene should look like. And I would expect, even if it has aged, that I still find the signature of polypropylene. So I need to,
Good way to test that is to find that box of,
yeah,
of those plastic samples, and they're all in Ziploc bags.
Yeah.
And you'll find some with PP written on it.
Yeah, I will do that. Yeah. So this is currently what I'm working on, and also you guys know that I'm working in the microplastics cluster. So that's a community of 28 professors and their groups working on microplastic issues. So I'm very involved in organizing a lot of workshops in that regard. So I'm organizing journal clubs, which takes place for students supposed to every 2 weeks. So if somebody is interested in microplastics, you can join anytime. And yeah, we're also organizing workshops for like yeah, strengthening the network between the cluster members. And also there's an idea evolving like between Matt, me, and Lori and Marcus Chance that we may conduct one joint microplastic study, where because Lori has thousands of different kinds of microplastic samples. So we are currently brainstorming on whether we could choose a specific sample, and people who are interested in the cluster would analyze it with their method of choice, and we could like yeah, create a joint project. So this is something which is evolving right now, and I'm working on.
Good. Yeah, and we'll have to think of the scientific problem that's at the heart of it. What is the relevance of the information? So, I mean, you're just starting out.
Yeah, yeah. As to start with plasma side, and not much to provide, but I have some questions to ask, and if we can.
Yeah, we can sit down and talk about
Is it possible to add omega-3 to the system and then see what happens?
I'm sorry, to add.
Omega-3. Yeah.
Oh, yeah, oh, omega-3.
Yeah.
I'm sorry, I didn't hear. Yeah,
Yeah.
definitely. In fact, we want to add omega-3 and omega-4. So we want to do some things with multiple colors, and there also, I would love to be able to extend to other, now that we've seen this characteristic scale invariant behavior, it'd be really interesting to know if other systems, different molecules that have different molecular weights and different dissociation characteristics, if they would show the same scale invariance critical exponents. And so for that, we need different excitation schemes. I should mention, so we're back on plasma for just a minute, and I'll mention I had a telephone call this morning with Dave Chandler at Sandia. So Dave Chandler has been in this business as long as I've been in this business, and is a really very entertaining and dedicated scientist. He's really a good person to know. You know, he's a nice person to work with in the lab. And he's famous for doing something called velocity map imaging. So this is where you take an expanding sphere of charge, and particularly if it's electrons, you can use electrostatic optics to project that onto a detector, an imaging detector. And from the rings it forms, you can deduce the velocities of those electrons, the velocities they had at the beginning. And so this is used for electron spectroscopy, to do photoelectron spectroscopy. But he does many other things as well. And he's determined to build up a big program in ultracold plasmas. And so he wants our advice, and he wants to collaborate. And so I think we will certainly have lots of good discussions, and you know, I think this will create some opportunities. Okay, Matt, what's going on with you?
I'll start slightly at the beginning, just because there are some new people here. So I'm working with Sepida Pakpour at UBC Okanagan, and she's sent us some samples of airborne everything really, but there may or may not be some micro nanoplastics in it. And so I've been trying to implement iSCAT to use as a characterization tool for these samples. And so I've implemented some of the tools that Luke's developed for looking at the gold nanoparticles. But the samples that I have are just much more complex, and so I've had to build up that quite a bit. In my work, there's a lot of image processing and computer vision type stuff to be able to identify when we have a plastic landing or any type of landing on it, really. And so what I found over the past year or so is that, I guess like one thing that lacks quite a bit in the system that I have right now is that even if you can see a landing, you don't really have any idea what it is. Like if we're dealing with gold nanoparticles, it's great because every landing, it's got to be a gold nanoparticle. But once it's a natural sample, it really could be anything. And so we've tried to use some of the tools that we have and just exploit them to the furthest extent that we can to make some discrimination. So one of the things that we have is these positively charged lysine cover slips. And so there was some thought put into maybe just that alone. I mean, they already have a selection bias because it will only bind to something that's negative. And so maybe there was some potential there for being able to do some sort of in situ separation. And there is some, it does work somewhat, but the systems are just much more complex. That having just a binary selection basis isn't quite enough when you have really an innumerable amount of things. You have no idea what's in it. And so there's been just a lot of motivation to actually get real chemical identification. And so currently what I'm working on is trying to put confocal Raman into the iSCAT system. And that's just what I'm in the middle of right now. I'm getting the optics set up. Kara's helped me a little bit on that. I kind of got her feet wet on the optical table, so she's starting to get used to that a little bit. Teresa's helped me a little bit on that too. And I think it's going pretty well. So, just takes a little bit to get everything set up. But yeah.
That's going to be fantastic. It'll be a unique system. There's no other system like that in the world. So it's definitely worth pursuing and then applying. And the idea is that if you have a system and it's completely static, so nothing moves, and you record all of these iSCAT landings, and every iSCAT landing appears and then disappears with the way the signal is processed, but the particle is still there. And so after you finish an iSCAT experiment, you know the coordinates of every particle that's landed. And so if you know where your Raman focus is, you now can move your system and go to every particle and take an image. And I think that this is a place where right at there's an edge where things are still quite good for iSCAT, but still big enough to see for Raman. So 200 nanometers, for example. 200 nanometer iSCAD produces a big signal, but yet it still is ratiometrically discerned. I mean, it disappears. It doesn't take up so much room on the cover slip that you can't run a very long experiment. So we record, maybe 200 bandings of 200 nanometer particles, and then go in, and the confocal waste of a human neon laser beam is not much bigger than 200 nanometers. And so you just focus right on a particle and collect the chemical information. That'd be astonishing.
I agree. We'll see how it goes.
It's exciting. So hold on, what are you up to?
Okay, the project when I joined the group was determining the crystallinity of pulp sheet by using Raman spectroscopy instead of any other method that would destroy the crystallinity of the sample when it's like being prepared for that technique. The golden standard in that area is XRD, which particles need to be under 10 micron to be able to get a random orientation. Otherwise, the result would be angle dependent and it cannot represent good data of that sample. So we tried several different methods of micronizing, such as spray drying and different type of grinders to get that to that size, but it was not very successful. So we decided to switch to another approach to extract the CNC, which is cellulose nanocrystal, from that pulp sheet and measure the yield of this chemical extraction from that pulp sheet, and then relate the Raman spectroscopy to that quantification. So that's one of the projects that I work on there, and I work on two of the service projects that are from Camper. And another thing is that I was also using the iSCAD for determining the size of these cellulose nanocrystals. But the problem with CNCs are that they are not as like the electron density in these particles are not as high as gold nanoparticles, so the scattering is like smaller, and also they are not like nanospheres, nanorods, and they are very small in one dimension, 2 dimension, very long on the third one. This results to a very small scatterings, and it makes it hard to see on ratiometry measurements. The idea that I got from the seminar in Victoria was that to employ localized surface plasmons to enhance the scattering in the iSCAD and to might be able to see the very small CNC particles that are in range of 50 nanometers. And another project that we started recently is to is a kind of trick to detect the noise and fixed pattern and fluorescence in a Raman spectroscopy to be able to get this Raman signals out of data that is mostly the fluorescent with various weak Raman signals by applying LED as a light source to get all these noise, fixed pattern, and fluorescence, and then get the Raman spectrum with laser and do some data processing afterward to get the Raman spectrum.
All of those are very, very important experiments. I think that the CNC experiment, that is to say, the first one you mentioned about developing this classification model. The difficult part of that as you pointed out, is to do the chemical extraction and try and determine by wet chemistry. And that is very often the case with that's almost certainly true for every machine learning problem worth doing. There's an easy part, which is the machine learning. And there's a hard part, which is assembling the data set that you need that serves as your ground truth. And it's almost automatic that your ground truth is going to be very, very difficult to know. Otherwise, it's not worth doing machine learning. So if the measurement is really hard to do, the harder it is to do, the more valuable the machine learning method gets. And so since your aim is to be able to just point at a piece of paper or point at a pulp material and say, oh, 26% CNCs, since that's your goal, it's so much easier than the alternative, which is to take all of that pulp and make CNCs out of it and finally weigh them. It's very, very hard, but you have to do it one time at least.
Hopefully.
Yeah, hopefully. Yeah, I'm very interested in how it develops with the ISCAT cellulose. We've seen papers recently where people have used refractive index information or polarizability tensors to try and calculate. Vahid Sandahar is very big into that. Try and calculate the magnitude of ISCAT signals. I think it's going to be something we want to do in the anisotropy of the CNCs makes it quite interesting. So there could be some really fancy modeling to be done. But Ginger, I know you're working on the fluorescence side in addition to the applied aroma. So what have you been up to?
Yeah, so the project that I guess I started this group in is the Terramera project. Sarah already explained it, but basically we're trying to use a digital lock-in filter and also a special hardware with dual modulating lasers to illuminate soil samples and get information out of it, like sequestered carbon or fixed nitrogen. Ultimately, this is going to be a field portable instrument. So our Terramera, which is located downtown, they've already built a couple of field portable instruments, but right now where we're at is there's a lot of questions regarding the soil, regarding how exactly the digital lock-in filter is going to work. There's just a lot of properties of the soil and its fluorescence that just keep coming up the more we kind of dig into the issue. So I kind of focus on the hardware side of things. I'm making sure that the instrument is just, we can get as much signal out of it as possible. But more recently, I've been interested in the fact that one of our main assumptions of our digital lock-in filter is that the fluorescence doesn't really change. But what we're finding is that the fluorescence is changing. There's some photo bleaching and a lot of other effects that are occurring. And just today, I actually, there's really interesting kinetics of the photo bleaching, just because there's many components of the soil that are photo bleaching or reacting at different rates. So that is a new issue that I'm focusing on. And then very related to fluorescence is the project with Human, where we are illuminating, basically what we're going to do is get the Raman plus fluorescence and then just the fluorescence signal and then subtract that fluorescence to end up with the Raman.
So eventually, if you can do that in real time, that would
Yes.
really be nice, because then if your fluorescence is wandering, you'll keep up with it.
Exactly.
Yeah.
Yeah, so I think that those two instruments and the methods that we're going to develop are going to be really interesting to compare to each other as well. Yeah, those are the main things.
Great. Kara, you're just getting started.
Yeah.
So you've had your hands into the confocal Raman.
Yeah, I'm at the training for the optic.
Is it making sense?
Yeah, I think so. It's a lot to take in, but yeah, I'm getting there.
Yeah, it's very important to define the focal point with as much rejection as possible. So you only want to image that that plane of focus, nothing above and nothing below, because certainly below contains a lot of signal glass, you might not see, especially with small particles. Good. So Kevin, I know that you're focusing on writing mostly.
Yes, I am. I am writing mostly, and as I told you on Friday, I did have a little bit of progress. And as you know, I don't know if the other members of the lab know, one of the dye circulators for our omega-2 laser stopped working a couple of weeks ago. So I was working last week with Benny, making sure that it was working. So I think it is working properly. However, I cannot remember if I turned it off before I left. So I'm probably going to text Roche after this meeting is done to make sure that the dye circulator is off. So thank you for your help, Roche.
It sounds still on, so I'll try to.
Oh, yeah. When those motors, we want them to last as long as possible.
Yeah.
Definitely will turn that off.
Yes. But yeah, that's it for me.
Okay, well, and you know that I'm working with Smilla to try and get a little more information about your omega-2 spectra out of simulations. And I'll keep you posted on that. So that's a dimension that we don't really all have to fret about here. But when it's done, I'll be very proud to show you, but I won't talk about it.
Sounds good. Fantastic. Thank you, Ed.
And Masa, so you're processing data, right, with your work with Natalia at Terramera.
Yeah, so first of all, I'm sick since I received my third promotion dose of vaccine. I'm sick since then. I don't know why it's going like that. I should have not get that vaccine. Anyway, so yes, right now I'm focusing on the data processing part, but in general, I've also kind of started my research with a simulation about this Terramera project. So the motivation is quite exciting. There is this carbon sequestration phenomenon that is happening and is quite promising for the environment, that this carbon in that atmosphere can be absorbed through regenerative agriculture to the soil, but so far it's so few that they can measure this absorption. So this development and this applied technology is a method that promise a way that we can measure the amount of carbon has been sequestered in soil, but soil is one of the most complicated environments. It's so fluorescent for a sensor or like Raman, and this applied methodology that used the dual laser modulation was a quite interesting project to start with. I started with the simulation, and we've proved that there is possible in theory and in mathematics modeling, it's possible to make the contribution of fluorescence constant, and then we remain with this Raman spectra, which is oscillating with a specific relationship. And if we applied a demodulation method and the remaining remaining Raman plus noise, after we remove that constant or DC fluorescence, we can get some signature out of it, and then build that classification models to correlate that with the amount of carbon, phosphorus, nitrogen, and other interesting elements in the soil. So it was very interesting. I've learned a lot, and we are in a very critical moment. At the beginning, we wanted to use a locking digital filter, which is a signal processing approach. And we made quite a bit of success on that. It's working on a single sinusoidal noisy wave, but to extend it to a larger case like Applet. Applet is a 2D data. It's like, so if you know the Raman spectra is just a frame in wavelengths and intensity, but we get in time dimension, we collect tons of many more of these a frame of Raman spectra. So there is a 2D Raman spectra one time and one wave number. And recently I want to go through some data has been collected. We don't know yet what they look like. I'm going to look through them and trying to build up an autoencoder, which is not a signal processing, but a machine learning approach that seems to be very promising and very strong to help with noise. Contributed to the roman that we are interested in. But in parallel to this, I started off from a built up approach of building some synthetic soils and process them using conventional Raman spectra. Now I've made a mixture of amino acids, mixture of 6 different common amino acids in soils. And I took a conventional Raman and IR of those samples, and I'm in the middle of processing those, because as much as I learned here, I can apply it in the future, because we want to extend this, as I mentioned, it's a bottom-up approach, and I'm going to add some minerals and other components to that, and see what's the effect of heterogeneity and homogeneity is on conventional Raman, and these can be used as a grand truth simple samples for our applied approach as well. So I'm involved.
Like many of the projects in this group, it's got a long-term, very basic, practical utility, but there's so many elements of it that have to work that are so demanding of fundamental progress. So there's a framework in which there's a lot of innovation and originality is required to make it actually happen. And I think that your standard edition samples, that's going to make a very nice paper, just a Raman chemometrics paper. I think is going to be, we'll be able to show how pre-processing and post-processing has helped you improve the classification accuracy in that particular space. I think that will make a fine paper.
Yeah, and I'm going to fuse this IR and Raman data. Both are vibrational or raw vibrational data, and just feed that data to the models that I already implemented and see what's the results is.
Sounds good. Okay, well, we're coming right up to the end of an hour, and I think we've covered everybody. We won't have to do this every time. But it's good that everybody had a chance to kind of give their perspective on what it is they're doing. And I think from here on out, why don't we just try and we'll have a bit of an open discussion, new things that might have come up or anything that someone wants to talk about, but then have a brief presentation. Somebody talk about something that they're eager to talk about. And we'll just use the group meeting for that. And if it turns out that it's short, that's fine. You can meet for 15 minutes. That's nothing wrong with that. But whatever it is, we've got this block of time, and let's get together and have a cup of tea and sit down. Any other issues? I did. I talked just outside the door before the meeting started. I spoke with Ken McFarland, and he claims to have taken those pictures himself recently. And it's a coincidence if that picture sort of looks like our lab, but it's really another lab. And I think that might be what it is. What they want to do is they want to put little angle iron braces at the bottom of the cupboards. And the one place that's going to be a challenge for us is where the BX51 is right now. And what we'll have to do is watch for the carpenters when they come in. They're willing to work around us, and they recognize that they can't disturb an instrument or get it dirty. So what we can have them do is just screw in the wall far away from there and make sure they protect everything.
Is this just for the cupboards or the cupboards and the shelving?
So the shelvings, they've determined that those are strong.
Okay, because the microscope is just under the shelving. So we,
Okay, good.
so I
Then-
think
then
we're
we're
okay.
Okay. But even so, I mean, just getting in there and doing any kind of impact drilling in the concrete blocks is not good for the optics, so we should talk to them about what has to be done.
We have a protective cover for microscope as
Okay.
well. So be sure to put that on.
Do we know when they come?
No, we don't, but Ken is good. I'll have, Ken just raised the issue with me.
Okay.
So I haven't heard anything about it. Or firm plans. Okay,